Hello, good morning, good afternoon, good evening, people of Earth, and welcome to our SETI Live. My name is Franck Marchis. I'm a senior astronomer at the SETI Institute, and today we are going to talk about the mysterious Planet 9 or Planet X, whatever you want to call it. So to talk about this interesting planet and some recent development in the study of this hypothetical planet, we invited Kevin Napier. Hi, Kevin.
Hello, thank you for having me.
Thank you for joining us. So Kevin is a physics PhD candidate at the University of Michigan. That's the reason you have this hat, right?
Yeah.
Yeah.
That's the only reason.
Kevin studies solar system dynamics and is interested in understanding the details of the solar system formation and evolution. So he has a paper that's been published recently or accepted recently, into which he describes some kind of interesting results on the existence of Planet 9, result that seems to imply that the gravitational effect we have seen on the planet, on the Trans-Neptunian objects, it's in fact an artifact or a selection bias. So we are going to talk about that, but the consequences of this, and I'm going to say the end of the story here, is that Planet 9 may not exist, in fact. Okay, so before talking about the details, if you are watching us right now on YouTube, Facebook, Twitch, or any other social media we are streaming, let us know where you're watching us from, and let's dig into this interesting story. So, Kevin, first of all, what is Planet 9?
So Planet 9 is a hypothetical planet in our outer solar system. It's about 10 times the size of Earth, between 5 and 10. And it orbits at about 500 times the distance from Earth to the sun, right? So that's called 500 astronomical units, or like 20 times as far away as Neptune. The idea is that this object that's orbiting so far away from the sun has been able to elude our discovery so far because it is so far away and would be so faint, but that it has gravitational signatures in the smaller bodies of the solar system that we have been able to discover so far.
So when you say we have been discovering this by gravitational interaction, what exactly do you mean? What do we see?
So there's, I will share my screen actually, so I can
give
a little bit of background. So out beyond Neptune, at about 30 astronomical units, if we remember that unit from before, there's this belt of objects called the Kuiper belt. And so far there are about 3,000 known objects in this belt. And this is a top-down view on the left, and this is an edge-on view on the right. And of these 3,000 objects, there are about 20 that show behavior that is very difficult to explain in the absence of Planet 9. And those are in red here. So if I plot their orbits, these are the orbits of all of those bodies look down from the top, right? So it looks to the naked eye like there's a clustering, like there's a preferential direction in which these orbits are pointing that's kind of along this axis. And it turns out that Planet 9 can induce that kind of clustering. So
go ahead.
No, go ahead.
So this was discovered, in 2016?
So the idea that there's a massive planet out there, well, that's always been around. But this particular one was put forth in 2016 by Konstantin Batygin and Mike Brown at Caltech. But
yeah, I want to remind the context here, because those Kuiper belt objects that you mentioned, the first one was discovered in 1992. So this is a new type of population of small solar system bodies. And I'm amazed when I hear that we have discovered 3,000 of them. And the point is that they're so far away from us that when we study them, we also study the distant solar system. And that's the reason we had to wait 2016 to have a paper that claimed the existence of Planet 9 from the distribution of orbits of those most extreme ones. Right. They call them Extreme Trans-Neputnuan Objects.
Right. So the first of these Extreme Trans-Neptunian Objects, I think, was discovered in 2003. So even a decade after we discovered the Kuiper belt.
So in the paper by Konstantin and Mike Brown, they did this analysis with an handful number of extreme trans-Neptunian objects. 6 of them, if I do remember properly, right?
Yeah, 6.
Yeah. So what is new in your study?
So since then, there have been about 14 of these objects discovered. And the biggest issue with their original study, so that they showed that it's true that a massive planet like the one they proposed could cause clustering like what we observe. But what their study didn't take into account is why we observe what we do. So what we correct for in our paper is this effect called selection bias, which means that when you're looking at the sky, you can only see to some depth, right? You can only see just so faint, and you can only see things where you're looking. So if you aren't looking everywhere, there will be some bias in the discoveries that you make. And that bias is extreme in these objects. It's fitting because they're extreme trans-Neptunian objects, but it's because they're on these very long, skinny orbits. They basically come in, they make their closest approach to the sun at 30, 35, 40 AU or something, and they turn right back around. And so the functional form of how the brightness of these objects goes is like 1 divided by r to the 4th, where r is the distance from you to the object. So that, all that means is that they get faint really fast as they're moving away from you. So you can only see them when they're really close to perihelion, when they're making their closest approach to the sun. And it just turns out, so I'll share this slide again. In my slide that I showed here, that closest approach is one of the variables that shows this clustering.
Mm-hmm.
So what you need to do is you need to assemble a large enough sum of these objects that have been discovered by surveys where you can correct for the observational bias. And that was the new thing that we did in this paper. Now that's been done in a couple of other smaller papers, but ours was the first meta-analysis to really put a convincing number forward.
So I read your paper, and so you basically use data from various surveys. The Outer Solar System Origin Survey, called OSOS. This is conducted in Hawaii, if I remember right, on the CFHT.
Yes, it was.
It's a 4-meter class telescope. There is 5 objects from the Dark Energy Survey. This is a telescope. It's which telescope is this one?
It's the Blanco in Chile at Cerro Tololo Observatory. It's also a 4-meter telescope.
It's also a 4-meter telescope. And then there is 4 objects from a survey conducted by a colleague of mine, Scott Shepard, Chad Trujillo, and David Tolan. And for those, they use what kind of telescope? Do you know? Do you remember?
They use whatever they can get, really. But they're all very impressive telescopes. They use the Large Binocular Telescope. They use Magellan. They use the Blanco, and they use Subaru, which is the best telescope on the planet, right?
Some people in Japan will be happy to hear about that. Talking about Japan, so we have people watching us right now from the Silicon Valley. That's not far away from me, but also from Australia. That's much further away. Florida, Liverpool in UK, Italia, Montreal, Ohio, Turkey, Brazil, San Diego, Montreal again, Philippines, Southern UK. I didn't know that was a country, but why not? Chicago, Germany, Michigan, Washington, D.C., Pennsylvania, Moscow, Russia in Moscow, and Meerut in India. So welcome, and thank you for watching us. So today we are talking about Planet 9, this hypothetical planet. And Kevin here is describing his work he has done so far to infer or not the existence of Planet 9. So what's the conclusion of your paper from this analysis?
So the conclusion in a sentence is that while we cannot rule out the existence of Planet 9, we can say with certainty that it is not required to explain the data that we have from the outer solar system.
Because the distribution of those orbits, when you had all these other targets, all these 14 extreme Trans-Neputunian objects, it's basically not clustered in one area. It can be it's more distributed. Is that a discrete understanding?
So they still appear to be clustered to some degree. That clustering is widening as we get more data. So the evidence is, depending on who you ask, the evidence is getting weaker. Some people say it's getting stronger, but that's not necessarily true. But so when you correct for the bias, you find that some of the surveys that have discovered these objects are only able to discover objects in or near this purported clustering. So if you're only looking out of your window, you will only see trees out of your window. And then so you could say, oh, there are only trees right there. Or you could say, well, maybe there are also trees everywhere. And so that's what we can't distinguish between. But the null hypothesis would be, yeah, there are trees everywhere. There's no reason to believe that there wouldn't be. It would be convoluted to think that a lumberjack went around and knocked down all the trees that weren't just right in front of your window.
Except the one in front of your windows, yeah. Oh, interesting. We have someone who's joining us from an oil rig in the UK, so probably in the North Sea. So I don't know who you are, but welcome from this place. You are watching the SETI Live and listening to two astronomers talking about Planet 9. And also, thank you very much, Sabine Hens, for sending stars. We received them, and the more stars, the better, because, you know, we astronomers, so we like stars. Okay, so this is a very interesting conclusion, but it's not a conclusion that people really like to hear, right? So
yeah, that's true.
Can you tell us, I don't know, you are a great student, you wrote this paper with your team. There is several articles on this. So what was the reaction? What did you hear after the publication of this paper?
So we were writing this paper for about 2 years. And it took that long because, you know, I'm a lowly grad student. And when I started, I had just finished undergrad. And we wanted to be completely positive that my result was correct because we knew it would be controversial. So right away, the morning that the paper was posted on the archive, that's the free preprint database where you can post to, there were dozens of people on Twitter hailing that Planet 9 is dead, like the Munchkins and the Wizard of Oz coming out after they melted the Wicked Witch. But there are also people who are correctly claiming that no, Planet 9 is not dead. But the degree to which Planet 9 is not dead is still being debated, right? Because this work might show that no, there's no reason to suspect that the ETNOs, that these objects are clustered. But there's more work to be done, I should say.
So in your paper, you give kind of a probability of existence. Can you give us this number of no existence?
So yeah, it's not exactly a probability of no existence. So what we do is we compute these numbers called p-values, which describe how consistent the data are with a uniform distribution. And we find using those values that you cannot reject that the data are uniformly distributed. And it's not even really close. It's something like 80% consistent with the distribution, something like that.
Okay, so you're a grad student, so this is a very high-profile paper based on the fact that I noticed it right away, for instance. And I think I contacted you on Twitter too when I saw the publication of this paper to invite you here to talk. So I'm assuming this is not the end of this research, right? What's the next step for you or for the community?
Well, I think that we have pushed the sample of ETNOs that we have currently as far as it will go. The next step is to discover not 2 or 3 more of these, but 200 or 300 more. And when we do that, you will be able to look at the data, correcting for bias, and say, either these are clustered or they're not clustered. And if they are clustered, that will really refine the predictions of where Planet 9 is. And if they are not clustered, then that's the end of the story. There's some other mechanism causing the other weirdness in the solar system, which we can get to after this. So the next step is discovering a lot more of these. So there are a couple of ways going forward here. One, in the shorter, more immediate term, is a survey that I'm involved with called it's called the DECAM Ecliptic Exploration Project. So we're using the Blanco telescope in Chile, and we're looking at a few different fields in the sky, and we're aiming to go extremely deep in our exposures. So rather than covering a lot of area, we're finding very faint objects in a small area. And we hope that we'll discover maybe, I don't know, a few, at least maybe 10 ETNOs in our survey. But what will really close the books on this is the legacy survey of space and time at the Vera Rubin Observatory. So that will survey the whole sky at an incredible cadence, something like every few nights. And moving objects, having such a cadence is very preferable for discovering moving objects, because you look at the sky one night and the object is somewhere, and you look at it again the next night and there's nothing there. So you can go back into your data and say, okay, well, there used to be something here, there's not now. Let me check nearby and see if there is something nearby that was not there the night before. And then you can link those observations together and figure out that, hey, there's something moving here. And that's an ETNO, that's a regular TNO, it's an asteroid, something got in front of the camera. So that should discover 100.
So that's the prediction, is that we should discover 100 ETNO with the Vera Rubin telescope. So that's this is going to have its first flight at the end of this year, I'm assuming, and the survey will start, and except this number of 100 is, I think, after 1 year of operation, 5 years of operation of the Vera Rubin. So maybe we can
all together.
Go ahead. Yeah,
maybe
we can comment about the existence of Planet 9 from others, weird dynamical or other phenomena in our solar system. Do you have maybe some ideas on that?
Yeah, so there are two really, really interesting problems in the solar system. They're far more interesting to me than whether or not the ETNOs are clustered. So as I showed before, there are, I'll share my screen so that people can get a good idea. Oh no, there it is. So this is an edge-on view of the solar system. So this is the plane of the solar system across here. You can kind of see it. And then up out of the plane, there are these dots, and those are high inclination objects. So beyond about 40 degrees or so of inclination, so beyond about here, we don't really have good models to explain how objects get on those sorts of orbits. So the most interesting of these objects is called 2015 BP 519. It's a very catchy name, right? But my group discovered it in 2015, and they wrote a paper about it. And it has 54-degree inclination. So it's orbiting like this in our solar system. And it's also a trans-Neptunian object, and it's detached from Neptune, meaning that it never comes within something like 7 AU. So it's really a mystery of how it got there. And Planet 9 explains its existence as well as anything. But that's just one object, right? It could have just been, there could have been some anomalous event, passing star.
Or something. Mm-hmm.
Yeah, there could have been a chance smashing together of ETNO or TNOs out there, something, who knows? But there are several such of these objects, none as extreme as the one I was talking about. But that is a central question, is how do those objects get produced? And then another question that really baffles is this one about, so objects come to perihelion, and that means that they're making their closest approach to the sun, and the distance at which that happens is called the perihelion distance. Now, most objects in the solar system will come to perihelion, within 40 or 50 AU or something. But after 50 AU, there's this drop off, for about 10 AU, and then there's one at 65 AU, and there's a couple around 80 AU, and there are like a few. There's a sparse smattering out beyond 50. And it's really puzzling as to why there would be objects with perihelion distances out at, say, 80 AU. There's no mechanism that can make them be at 80 AU and not also at 60 AU or something. So maybe there are observational biases. Maybe we just got lucky in discovering them. So Sedna is one of them, and Sedna is huge. It's really bright, so it's relatively easy to find. But so Planet 9 can produce those types of objects, but maybe there's something even more fantastic and wonderful that could have produced them. If Planet 9 is not there, whatever mystery has produced these objects is going to be interesting. It's sort of like, so for me, thinking about this problem is like when you're thinking about, well, what was there before the beginning of time? What was there before the universe started? It's how did it happen? It just totally doesn't make any sense.
Thank you. We're getting questions, and one question here about your personal reaction when you found out about this discovery. What was when you realized that is something here that could be interesting, could be published, and will be probably controversial?
At first I was skeptical, because you should always be skeptical of your own work. But once I continued to find my results, it was exciting, because it was a different result than what some astronomers that I really respect at Caltech had come up with, and my work was rigorous and it was correct. So figuring out why a result is different from other scientists is always interesting. And controversial, yes, it's controversial, but that's the whole point of science, right? You can't shy away from your results, because you know what your work was, and you know that you did your due diligence and it's correct. So yeah, that was never an issue.
So we have questions about Planet 9 itself. Can you tell us a bit about the planet, the mass, the distance it will orbit? And also we have a question about, is there more of this ETNO, Trans-Neputnuan object? Does it mean that there is the Kuiper belt is maybe way bigger than what we expect?
Yeah, so Planet 9 is a little bit smaller than Neptune. It's about between 5 and 10 times as massive as Earth. So if it's there, it's probably on a rather elliptical orbit. So it's not a circular orbit. So it comes closer to the sun and then moves farther away. And it would be at a mean distance of about 500 AU astronomical units, maybe a little bit more. And the next question was about more ETNO.
The mass of the Kuiper belt object. How many objects we think there is in the Kuiper belt? Or...
Oh boy. I used to know this number. I think it's maybe 100,000 or something, but we've only discovered 3,000. So the survey that I'm a part of right now, if all goes well, if the data are not contaminated too badly with junk, and if we can continue to get telescope time, which has been difficult the past year due to the pandemic, we will discover between 3,000 and 6,000 more Kuiper belt objects. So we will double to triple the size of the Kuiper belt.
Another question that come out: is there a plan to have a space telescope, maybe closer to Pluto, or maybe just in orbit around Earth, that could help for this kind of research?
Yeah, James Webb is something like a 6-meter telescope that they're going to launch into space, which is incredible. It will be even better than Hubble, but that's not launched yet. So it should be launched soon, although soon is not soon, right? Soon is whenever it happens.
October.
Yeah. Hopefully, right?
We shall see. End of October officially.
Yeah.
So that was my last question, and that's also the question of someone mentioned. So what about the reaction of the researcher like Mike Brown and Konstantin Batygin? I saw that there is a rebuttal written online and available. What do you think of those critiques and comments?
So they're skeptical, as any good scientist should be, right? So one of the things that Mike Brown is saying is that our uncertainties are larger than his, which is not true. Neither of us reported any uncertainties because neither of us could report uncertainties because we did not do a Bayesian analysis. We did something called the frequentist analysis, where your uncertainties that you can calculate are basically limited by how many samples you take. So the real difference between our works was how well we were able to model the surveys and to figure out what kind of objects they were or were not able to detect. And our model was better than theirs. I don't think that I am out of place in saying that. So I can pull up a comparison of these if you would like to see it.
Go ahead.
Here it is. So this is the comparison of the outer solar system origin survey for the same model of the Kuiper belt. So we use all the same objects, and we used the outer solar system survey official simulator, or they used that and got this distribution for their detections from the survey. This is what my survey simulator got, and this is what their survey simulator got. And I think it's pretty clear to see that this is more like this than that is. Mm-hmm. So as far as we can tell, that's the prominent source of uncertainty in the analysis, is how well you were able to model your selection function. And when you more carefully model your selection function, what turned out to be a 3 sigma clustering, so the 0.2% chance that it was wrong, turned into something like 1 sigma or less. So no evidence.
Yeah, I read his article, his blog post, and I was also surprised that he criticized your work, saying there is no error bar or uncertainty, sorry. And I don't see any uncertainty in their own paper as well. So it's kind of criticizing your work, but not using. It's weird. Anyway, it's a debate. It's a big deal because this Planet 9 is kind of this mythical object that we do need to explain a lot of problems we see at the moment in the solar system. And your paper is basically saying that it's not that obvious that we have in the dynamical distribution of this ETNO the existence of Planet 9. It doesn't mean that Planet 9 does not exist. It just means that this is not a proof of the existence of Planet 9.
Right. The evidence is not as strong as it was thought to be.
As it was thought to be. Exactly.
So there could be other things causing the weirdness that we see. So for instance, if there was like a Mars or an Earth-sized planet at 200 AU or something like that, we still would not be able to see it given our current technology. And it would still be wreaking havoc, causing, lifting things from perihelion. So creating objects like Sedna and VP-113. And it would still be causing objects to tilt on their orbits. So there are other ways that you can have mass hidden in the outer solar system and wreaking havoc to our models of the solar system. And it turns out that Mars-sized bodies are the most common things in planetary formation, right? So among the giant planets, things that are like sort of 5 Earth masses are the most common. But among the census of all of the rocks that get formed when a solar system is forming, I believe Mars-sized bodies are at least as common, if not more. Yeah. So a lot of interesting research possibilities.
So so in short, it's possible that we have a smaller planet, not a gigantic super Earth in orbit around our solar system. It could be that we have a smaller planet that produce these weird dynamical anomalies that we are observing now. We know Kuiper belt objects. Ultimately, what we really need to do is to see this planet, to detect it, of course. And that's a work in progress. There is, I forgot the name of it, but there is a program, a citizen science program to find Planet 9 or the equivalent of Planet 9 into mid-infrared data using NEOWISE. There is also a ton of astronomers trying to find this on archive data available as well.
Right. Yeah, it's all very important to do, because the more that we look for the planet, the more that we find other things, and the better we understand our solar system.
Okay, well, thank you very much, Kevin. Do you have anything else you want to say? What's the next step for you, for instance?
Well, I'm working on DEEP, the solar system exploration project I talked about. I'm also working on a few other dynamical things. So the capture of interstellar objects by our solar system. That's an interesting topic given Oumuamua and Borisov. And I'm working on a problem with the Earth Trojans. So Trojan asteroids are objects that are co-orbital with Earth, but they're not moons. They orbit sort of along Earth's orbit in a stable spot.
Good. So we're gonna hear about you again pretty soon. You may come back here at the SETI Live to tell us about your research.
Yeah, anytime.
Well, thank you very much for stopping by and telling us about your work on Planet 9. And I just would like to remind our viewers that next week we have a special SETI Live on women in astronomy with Cherry Ng and of the SETI Institute and Sida Ganju of Intel. They are going to talk with Beth. Beth will be the moderator of this SETI Live. And also next week, we have a SETI talk, and we are going to talk about the search for life on Mars using the Perseverance mission. So join us next week for this SETI Live and this SETI talk to hear more about the wonder of space exploration and the search for life in our galaxy. So thank you very much again, Kevin. I'll also remind you that we are a non-profit organizations. So if you like what you see, if you like what you watch, and you want us to continue to come to talk about planets, please support us. There's a ton of ways to do that. Joining our Facebook, YouTube, Twitter feed, clicking on like here, and joining also our visiting our website at SETI.org. And if you are motivated, you can also make a donation. We are nonprofits, and we do appreciate donation that help making programs like this one. Thank you again, Kevin, and see you soon. I hope to come to Michigan in the next 6 months when it is possible.